Apple presents itself as a company that has already crossed into the post-resource era. In its environmental reports, sustainability videos, and keynote presentations, the message is consistent and reassuring. Apple claims it is increasingly building the most complex consumer electronics on Earth using recycled materials. Aluminum is recycled, rare earths are recycled, and now silver is recycled. According to Apple, the future of high-tech manufacturing is circular, clean, and largely detached from the volatility of global commodity markets. But behind the confidence of those statements lies a quantitative problem that is rarely examined. Silver is not an abstract sustainability symbol. It is a physical input with electrical, thermal, and chemical properties that cannot be substituted at scale inside modern electronics. Every iPhone, every MacBook, every data cable, and every power management system Apple sells depends on silver and trace amounts that collectively add up to industrial scale demand. The question is not whether recycled silver exists. The question is whether enough of it exists at the required purity, in the required form, and at the required speed to support Apple's projected production volumes in 2026. To answer that question, the marketing language must be set aside. What matters are material flows, refining bottlenecks, scrap recovery rates, and industrial math. When those variables are examined together, a very different picture emerges. Silver is used in Apple products primarily for its unmatched electrical conductivity. It appears in solder pastes, conductive inks, multi-layer ceramic capacitors, printed circuit boards, camera modules, antennas, and battery management systems. These uses do not tolerate contamination. Industrial electronics grade silver must meet extremely high purity standards. Even small impurities reduce conductivity, increase heat, and raise failure rates. This matters because recycled silver does not emerge from the recycling process as a ready-to-use metal. It must be collected, separated, chemically processed, refined, and certified before it can re-enter electronics manufacturing. Apple does not disclose the precise amount of silver used per device, but industry estimates provide reasonable ranges. A modern smartphone contains between 0.2 and 0.35 grams of silver depending on model complexity. Laptops and tablets contain more. Data centers, accessories, chargers, and internal infrastructure add further demand that is rarely discussed. When Apple ships more than 220 million iPhones per year, even conservative estimates imply tens of millions of ounces of silver embedded annually across its ecosystem. Apple's 2024 and 2025 environmental progress reports state that a growing percentage of silver used in its products is recycled. The language is careful. It refers to recycled content in specific components, not across the entire bill of materials. It also avoids absolute volume numbers. Percentages sound impressive, but percentages do not reveal whether the underlying supply is scalable. The global secondary silver market is not a centralized pool waiting to be allocated. It is fragmented, inconsistent, and highly sensitive to economic conditions. Recycled silver comes primarily from three sources: industrial scrap, jewelry scrap, and photographic waste. Each of these sources has structural limitations. Industrial scrap is generated during manufacturing, not after product use. It includes offcuts, rejected components, and excess solder. This scrap is relatively clean and easier to recycle, but its volume is directly proportional to new manufacturing activity. It does not grow independently. It cannot expand to meet higher demand unless production itself increases, which creates a circular dependency. Jewelry scrap depends on consumer behavior. It increases when prices rise and consumers sell old jewelry. It decreases when prices are stable or when jewelry is culturally retained. Jewelry scrap also requires extensive refining to meet electronics-grade purity. Losses during processing are unavoidable. Photographic silver recycling has been in long-term decline for more than 2 decades due to the digital transition. What was once a major source of secondary silver is now marginal. Taken together, global recycled silver supply has averaged roughly 180 to 200 million ounces per year in recent estimates. This figure includes all uses, not just electronics. Jewelry, silverware, investment bars, and industrial reuse all compete for this pool. Apple is not the only buyer, and it does not operate in isolation. Now consider Apple's scale. Apple is not a niche electronics producer. It is one of the largest manufacturing operations on the planet. Its supply chain spans Asia, Europe, and the Americas. It operates on just-in-time logistics, with minimal tolerance for material shortages. Even small disruptions ripple quickly through production schedules. For recycled silver to cover a significant portion of Apple's needs in 2026, several conditions must be true simultaneously. First, enough scrap silver must be collected globally. Second, the scrap must be refined to electronics-grade purity. Third, it must be available geographically, where Apple's contract manufacturers operate. Fourth, it must arrive on timelines synchronized with Apple's production cycles. And fifth, it must not be claimed by competing industries facing the same constraints. This is where the narrative begins to fracture. Electronics manufacturing does not consume silver in a way that allows for easy recovery. Silver in smartphones is dispersed in microscopic layers, solder joints, and conductive traces. End-of-life recovery rates for silver in electronics remain low. Many devices are never recycled at all. They are stored in drawers, discarded improperly, or shipped to regions without advanced recycling infrastructure. Even when devices are recycled, silver recovery is not always economically prioritized compared to gold and copper. As a result, the majority of silver embedded in consumer electronics does not re-enter the industrial supply chain within a useful time frame. It is effectively removed from circulation for years or decades. This creates a structural lag that recycled supply cannot quickly overcome. Apple's reporting does not claim that all silver used is recycled. It emphasizes progress, not completion. But the implication many viewers take away is that Apple has largely solved the materials problem. That implication does not align with the physical constraints of the silver market. Primary silver mining remains the dominant source of supply. Global mine production has struggled to grow meaningfully over the past decade. Silver is often mined as a byproduct of copper, lead, and zinc. This means silver output responds to base metal economics, not silver demand. Even sharp increases in silver prices do not immediately translate into higher production. At the same time, industrial demand for silver is accelerating. Solar panel manufacturing continues to consume increasing volumes of silver paste. Electric vehicles use more silver than internal combustion cars. Grid infrastructure, data centers, and power electronics all rely on silver-intensive components. Apple is operating within this same tightening market. When Apple states that it is increasing recycled silver content, it is reallocating existing secondary supply, not creating new material. That reallocation has consequences elsewhere in the system. Other manufacturers face higher costs or reduced access. The system tightens, even if Apple's internal metrics improve. There is also a definitional issue. Recycled silver, used in Apple products, may include internally recycled manufacturing scrap. This improves sustainability metrics, but does not reduce net demand for primary silver. It simply improves yield efficiency. From a market perspective, that distinction matters. By 2026, Apple plans to maintain or expand production volumes across iPhone, Mac, iPad, wearables, and services infrastructure. Each incremental unit embeds additional silver that must be sourced. Even optimistic assumptions about recycling efficiency do not eliminate the need for large quantities of newly refined silver entering the system. The green narrative suggests a closed loop. The material reality suggests an open drain. This is not an accusation of deception. Apple's sustainability initiatives are real, measurable, and often industry-leading. But sustainability reporting operates in percentages and narratives, while supply chains operate in tons and ounces. When those two languages intersect, gaps appear. The idea that recycled silver alone can support the physical expansion of one of the world's largest electronics manufacturers collides with known limits of collection rates, refining capacity, and competing demand. The math does not collapse catastrophically. It tightens gradually, invisibly, and persistently. As silver inventories draw down and industrial competition intensifies, recycled content becomes less a solution and more a buffer. Buffers buy time. They do not create abundance. By 2026, Apple will still rely heavily on newly mined silver, whether acknowledged explicitly or not. The recycled silver narrative reduces headline risk and aligns with consumer expectations, but it does not rewrite the laws of material supply. The green mirage is not that recycling is ineffective. It is that recycling alone cannot scale at the pace required by modern industrial systems built on exponential product cycles. The conclusion is not philosophical, it is mechanical. Silver flows where it is demanded, constrained by physics, chemistry, and time. Apple operates at the frontier of efficiency, but even at that frontier, material limits still apply. The system works until it tightens, and when it tightens, narratives matter less than inventories.